So welcome to this class. So last class we have gone through the experimental protocols in atom probe tomography, and especially we also discussed about the Z, how to find the Z, and that is based on uh, the field evaporation which is taking place layer by layer. Okay, and that Z usually it directly relates to the atomic volume. Fine. So in this class I will show you some of the slides from my some of my colleagues or some of my friends who are actually scientists at BARC, and I would like to acknowledge them for these slides. So Deepak Arya is a PhD student at HBNI BARC, and Devdutt Shinde is a senior scientist in BARC. Okay, so coming to the so these slides, today's slides will just briefly go through the information which we are getting from the atom probe data, and how this information is used to determine the reconstruction of the needle specimen. Fine. So okay, so we see in this slide, as you can see, that there is certain appearance of contrast. Okay, and these are related to some kind of precipitates which are present in a matrix. Okay, so this is a matrix, and you can get this three-dimensional distribution of ions which are field evaporated. So this is a typical reconstruction. This is a typical reconstruction of the tip which is field evaporated. Okay, so as I told you, most of the reconstruction is done by reverse projection model. Reverse projection model. Okay, so you will get the information of X, D and YD position, and also the Z depth. Fine, and the color here, all the colors corresponds to the different species. Okay, so here you can see there is a precipitate which is actually with a high number density of these yellow color precipitates in a matrix. Okay, there are another kind of precipitates which are in the red color. Okay, so this shows that they have a different chemistry and they are distributed in a matrix. Now from the instrument, what we get the information. Okay, so first thing what we get is the sequence number. Okay, so if you have a needle specimen, okay, so the ions, the atoms which are polarized, they travel along the field lines, and layer by layer these atoms get accelerated, or the ions get accelerated towards the detector. So it is a layer by layer process. So it means that there is a sequence. So you can say that at the sequence 1, so the type of ion which is field evaporated has a time of flight about 200 nanoseconds. Okay, so these are the parameters which we get from the instrument: time of flight, the DC voltage which is applied, this is okay, pulse energy, we talked about the pulse energy, this is the XD position, YD position, and the number of ions per pulse. Okay, and the pulse skipped. Okay, so these are the information which we get from the a typical atom probe. Now if so, as it is a layer by layer process, there will be a sequence of atoms or the sequence of layers that is get field evaporated, like sequence 1, 2, 3, 4, and depending upon the type of ion, they have a different mass to charge ratio, and this mass to charge ratio, it is directly related to the time of flight. You can see that some species they have a 200 nanoseconds, some species they have a 19.8 seconds, means the time of flight is much less, so they are moving much faster, correct? So this is related to their mass to charge ratio. Fine. And DC voltage, as I told you that with the time the DC voltage increases. As you know that in an atom probe needle, the radius actually evolves. The radius increases as the experiment proceeds. So you are if you want to keep a detection rate constant, then you need to increase the voltage as per the detection rate for that particular needle specimen. Okay. Next is with this sequence, with these parameters what we get from the an atom probe, we can actually reconstruct those ions. Okay, so it means we can get the ion or the atom map in 3 dimension. For example, this is a particular material where you can see that the distribution of yttrium oxide as a molecule, you can actually also combine yttrium plus yttrium oxide and see their distribution. You can get the aluminium. Fine. So depending upon the species, you can select what type of atom map you need in that 3-dimensional volume. So your needle specimen will be like this, and whatever the analyzed volume will be there, we can reconstruct with these parameters. And to reconstruct, we need this data. Okay, heat sequence, time of flight, DC voltage, pulse energy, X hit and Y position and Y hit position. Okay, so briefly, with the one ion which is getting field evaporated, we have a time of flight of that ion, we have a applied voltage at that time, and also we have a XD and YD, which is the position on the detector. Okay, and what we want to know, we want to know the identification of ion and the original position of ion at the tip, which is a X, Y and also the Z. Correct? We'll come to that Z later. First we'll just briefly go through these slides with. Okay, so we need a model. Okay, as I told you, this model, it is nothing but a point projection model. Okay, and time of flight is to identify the chemistry or the chemical species. XD, YD, which can be converted for the XYZ of the position of those ions in the reconstruction. Okay, so this particular time of flight, this is just a revision. You can actually model it. So here there is a schematic where you can see that this is a needle specimen, and these having a certain atomic species, atoms, different color corresponds to different type of atom. Okay, and this is kept at a very base temperature of around 20 to 80 Kelvin in a ultra high vacuum chamber, and there is a distance between the L, distance between the tip surface and the detector. This is your local electrode. Okay, this is a hollow local electrode. So and there is a timer. Okay, so when you apply a pulse, either the laser pulse or the voltage pulse, one ion gets polarized, one atom gets polarized, and it gets accelerated towards the field lines, okay, along the field lines, and it hits to the detector at a position of XD and YD. Okay, similarly with another pulse, you will have another atom which is moves much faster, means it must have a low mass to charge ratio, and it gets hit to the detector. Fine. If there is another pulse, so in this matter, in this way, actually you can measure the time of flight by using the time keeper, where we can distinguish these chemical species or the atoms on the detector. Fine. Okay, so as I told you, the velocity of the ion which is traveling, it directly depends upon your mass to charge ratio in the electric field. Okay, so how to identify? So this is the basic equation, assuming that the atom leaves at an initial velocity of 0, so it has a certain potential energy on the tip surface. Okay, and that can be given by QV, and there is a total kinetic energy, and you know the velocity is L by T. T is the time taken, and with this basic equation, actually you can evaluate the mass to charge ratio of that particular ion. So in this way we can actually identify the chemical species. So we have discussed the mass spectrum. So this is a typical mass spectrum. These are the counts, and this is the corrected time of flight in nanoseconds, correct? So these are the identity. So you can see that these corrected time of flight, each peak corresponds to a single ion, single type of ions, okay? And we can range this, we can index it based on the time of flight, which can be converted to the mass to charge ratio, okay? So if you calculate the mass to charge ratio based on the time of flight, you can see that for a single element like chromium, you have a different charge ratios, correct? So for chromium you have a 1 plus, 2 plus, 3 plus. For iron you can appear for 1 plus, 2 plus, 3 plus. So you can have a different charge to mass to charge ratios for each species, okay? And the width of this particular mass spectrum, the width of the mass spectrum, which is m divided by delta m, this is related to your mass resolution, okay? And the number of ions can be counted by ranging this particular peak, okay? So in this way we can identify different types of ions. So these 3 peaks corresponds to chromium, and these 3 peaks corresponds to iron, correct? In this way we can range the mass spectrum. Now once we talked about the identification of the chemical species, now we will see that the position x and y, correct? So xy position of atoms. So in this we can see that after field evaporation, that particular red atom get polarized and ions and hit to some detector which is at xd along the field lines, okay? So ion trajectories will be independent of, you have to mass, charge and applied voltage, okay? And the geometrically they are shown as a hyperbolic in nature, okay? So in the last class we also told about the reverse point projection model, okay? Here the geometry, so usually in the last class I told you that if any atom which is present on the surface, okay, at the near field, usually they will field evaporate perpendicular to the surface, and as it moves away from the near surface, it gets compressed towards the axis of the specimen, correct? So with this, what point projection model, the Bass ETL method, you can assume that what the position so as we discussed in the last class, that if any atom which is present on the surface by the reverse projection model, it appears that this has to go along the field line perpendicular to the tip surface and hit to the detector, fine? But usually this is not the case. Usually at the near field it might appear that the initial travel of that particular ion is perpendicular to the surface, but as it goes towards the detector, these get compressed, okay? This is compressed towards the specimen axis, okay? So the final position will be these positions, not these positions. Based on this, what we can do is a simple reverse projection model. It was assumed that the final hit position of that particular ion can be regarded as a straight line which is passing through that particular atom on the tip surface, and it crosses to a position which is away from the center of that hemisphere, correct? So you can put as a center of the hemisphere. That point is called P. Okay, so a point P exists which maintains the same spatial relation between the tip and the detector. So this is the basic assumption in the reverse point projection model. Okay, now this particular distance from the tip surface to the P is related to the xi r, where xi is called the image compression factor. Okay, so with this we also talked about the how the detection is happening and how it is converted to the position of xd and yd. Usually xi is the image compression factor is 1 for the radial projection, which shows that it is perpendicular to the surface. If this is a stereographic projection, it is usually a maximum value of 2, the ICF values. Okay, so based on the simple geometry, you can see, so that there is another assumption that the particular atom which is located at the tip surface, which is going to be ionized, it is assumed that it is projected on the plane perpendicular to the tip axis. Okay, and based on this triangle symmetry, we can get as a d by xi r, is related to your magnification. Okay, so d by d is magnification, which is given by L by xi r. Okay, L is the distance between the tip surface and the detector. So your magnification becomes this formula. Okay, so for each position xd and the yd, we can actually, the x actual can be measured by xd divided by m and yd divided by m. Okay, so this is how the two coordinates x and y can be obtained with this reverse point projection model. Now I will just briefly go through, even though we have explained the determination of ICF and the radius of curvature. So ICF can be obtained by using film or by using pole figures, correct? So here there is an ion map which shows the distribution of ions which are hit to the fluorescent screen. Okay, and you can see there are several number of terraces, and you can see that the concentric rings which corresponds to the poles. Actually, from the stereographic projection, you can actually measure these poles and these poles. Okay, so in the field desorption image, this is the field desorption image, you can see that the appearance of these poles as a low density regions. Okay, and these are called zone lines. This is exactly related to your it can be related to your Kikuchi pattern, or you can create or the stereographic projection. Fine. So you can index these poles as per the symmetry. Okay, and these zone lines corresponds to these lines. Now you can say that if there are two poles P1 and P2, okay, and the distance between these two poles on the detector is d, so the angle between these two is related to theta p projection. But you know that P1 and P2 has some crystallographic orientation, and they have a certain definite angle, crystallographic angle, correct? That can be deduced mathematically by cos theta. Okay, so this theta p, with the triangle, we can assume that it is related to the d by L. Okay, and we already know the theta c, which is a crystallographic angle between these two poles which were indexed, correct, by cos theta. Fine, and so the difference, the ratio between the theta c and theta p is equals to the ICP, image compression ICF, image compression factor, which is a xi, correct? This is how we measure the image compression factor. Now, how to find the radius? Okay, so here you can see that the radius, as in the few classes back, as I told you, while the field evaporation is taking place, actually your radius is evolving, and the radius is increasing from R1 to R2. Okay, so to make the detection rate constant, you need to make the voltage also increased. Okay, so this is just an SEM image where you can see that the radius is not constant. It increases as we move away from the tip surface. Okay, so based on the radius, you can see that initially the voltage required to maintain a constant detection rate is lower, and as the radius tip increases, your voltage required also increases. Correct? So your tip will be very sharp here. It will be little bit blunted. It will be blunt. The bluntness will increase as your radius increases. Correct? And you know that if you assume that the electric field of the tip surface, if it is equivalent to the evaporation field of that particular atomic species, actually we can find the radius at that particular moment by putting the voltage divided by the kf, which is the field factor. Okay, and remember the voltage for HV pulsing, it will be the DC voltage plus the pulsed voltage applied. Okay, so this is how we can assume we can actually calculate the radius of curvature if we know the field factor. Okay, so now the next thing is how to find the K factor. Okay, so K actually is a geometrical factor. As I told you, it relates to the strength of the field at the tip to the voltage applied. Correct? And it depends upon the tip radius, shank angle, counter electrode distance, detector distance, and chamber shape. Okay, so if there is a small sphere of radius r and L, so the field factor is actually 1. Okay, and for the K usually varies from 2 to 8. Usually in the needle specimen. So how to estimate K? For estimation of K, I'll come in detail little bit of in the later class. So this is just an example where this is an iron chromium alloy. Okay, so where they will get the alpha prime precipitates. Okay, these are all BCC precipitates, and they know that these are all spherical in nature by using the alternative microscopy techniques. Okay, so they know that in the matrix of iron these are spherical precipitates. Now if you do the field operation of this particular alloy, then what will happen? You can actually get the reconstruction with different K values. Okay, so here you can see that with the 3.7, 4.7, 5.7, 6.7 and 7.7, and you can see that at the 3.7 these precipitates are actually compressed along the z-axis. That is different from your image or the expected precipitate shape. Okay, so but at 6.7 and 7.7 you can see that these are elongated along the z-axis. Okay, so the K factor from here we can, from the microscopy image, we know that these are spherical. It should be between, it should not be so low as 3.7 and it should not be so high as 7.7. And with the 5.7 of K factor, you can see that these precipitates appears as a spherical precipitates, which is most near to the expected one. So this is how the field factor can be estimated. There are other methods also to estimate the K factor that will come into the in later class. Okay, so this is how we can estimate the K. So now what we know the voltage, we know the path length, we know the evaporation field of that particular species or your tip surface. You have a ICF, you know the K factor ICF from the crystallographic axis, crystallographic angles. We can measure K factor by using the other microscopy techniques, and we can measure the K factor. Now we calculated the radius evolution, the tip radius of all time, which is related to the voltage K and F. Okay, we have magnified, so we have calculated the magnification by using from a definite R value, which is xi and L. So magnification is related to L by ZR. Also we can we have detectors, the delay line detectors are used to know the XD and YD position. But we need to find the Z, correct? So as I told you, this is a sequential process, correct? So in this sequence, you can see that this is a table where I have shown in the first slide, where we are getting all the information from the atom probe, correct? So here the time of flight, this is for the identification of chemical species. Your DC voltage, this is for the reconstruction and the evolution of the radius, correct? And exit and Y heat positions, these cannot be used for the Z. Your pulse energy and number of ions cannot be also used for the determination of the Z, correct? So now the only remaining is the sequence number, which is very important for the Z. Okay, so in the last class we have detailed way we have discussed about how the atoms are field evaporated sequence by sequence, correct? So with this sequence, actually we can actually assume we can actually calculate the Z evolution of Z with the during the field evaporation. Okay, so this is an ion. So this is a schematic where you can see that this is a needle specimen. Okay, and the color corresponds to different chemical species. Okay, so if you apply the pulse, then the atoms are polarized and get accelerated towards the detector in a sequence way. So you can see that in the first sequence, the atoms got field evaporated first, then after that the second sequence, correct? So it doesn't appear that the third sequence will field evaporated first and before the first sequence. Okay, so with this assumption, we can actually calculate the Z. Okay, so the position of heat detector can determine the X and Y, correct? So if the top layer has a 10 ions, so if we count this number of ions which are present, then I will be knowing that how the what is the 11th ion which will be from the next layer. Okay, so first all these ions or the atoms has to field evaporated, then only there will be a second set of atoms which are sitting gets field evaporated. So this is called sequence 1, this is called sequence 2. Okay, now so which each, so this is your reconstructed. So now you can see that how the relationship between the delta Z and the sequence of ions will go on. Okay, you can see that in the first there are 4 ions. Okay, and these 4 ions which gets field evaporated first, after that only there will be a second sequence and there will be a third and the fourth sequence, and these can be filled, correct? So this is in the 3 dimension. Okay, so you have a needle specimen. Okay, this is actually an area. Fine, this is actually an area related to X and Y. Okay, so by determining the atomic volume, we can actually relate to the XY and also the cross of delta Z, which is equals to delta V. It is nothing but the number of ions into volume of each ion. Okay, so with this atomic volume, actually we can easily estimate the delta dz, means the depth increment during the field evaporation. And in the last class we have derived some of the basic equations which is directly related to the atomic volume. correct. Now this is a schematic of a needle specimen, and you can see that based on the sequence, you can see that the red color will have a first to evaporate, yellow is second, and third is the green color. So with this way your depth is increasing, correct. With this way we can measure. So this delta z is nothing but the area of xy into delta z, which means the number of ions into the volume of each ion, correct. So this delta z equal to n into atomic volume divided by area of x and y, that cross sectional area. And this area of cross sectional area, if there is a detector here, and it corresponds to the demagnification 1 by m square of that particular area, detector area. So it is nothing but the area of the detector divided by the m square, which is the area of the xy, which is the analyzed volume, correct. So this way we can measure the analyzed volume. You know that the magnification is given by L by xi r. R can be given by V by kf. So with this equation we can actually estimate the delta z with this particular equation, which we have also shown in the last class. Okay. So now here one more variable here it has to be added is efficiency, because not all ions which are field evaporated are detected. So there is a detection efficiency is associated, that is related to your detection efficiency, and that comes into the picture of 1 by xi. Okay, so this is just a revision of how z all can be is determined along with the x position, y position, and the chemical identity of the particular species from the needle specimen, correct. So this is a one slide where I want to show you that how these reconstructions are so powerful. So actually we can resolve the atomic planes by this reconstruction protocol, what we described recent now. So here you can see that this is a small volume of a big data set, where you can see that these ions are actually arranged in planes, correct, and these planes are nothing but the atomic planes, which has a certain d value. Remember that the DHKL, this particular DHKL is larger than the penetration depth of the electric field, which is around some picometers. This is much less than the d spacing of that crystallographic plane, correct. So that's why we can actually resolve the atomic planes, and we can get the composition of each atomic plane in the z direction. So this is the we can call it as a it is a resolution along z, or we can call as a lateral resolution. Okay, so with this I will end this class. So in this class I have briefly gone through the different types of parameters, and also briefly we have gone through again with the z with some schematics, where you can understand that how the reconstruction is done based on the data which we are getting from a field evaporation in an atom probe. So here the time of flight, position of x and y, the voltage, evolution of the radius, and also the parameters such as pulse energy. These all parameters are used to reconstruct. And the z, which is reconstructed by calculating the atomic volume. Okay, assuming that the the field evaporation is taking place as a sequence by sequence, and based on the conditions, temperature, and the pulse and the HV or all the pulsing conditions, actually you can resolve the atomic planes. The resolution of atomic planes is possible because the penetration depth of the electric field is of few picometers. So actually you can resolve the distance between the atomic planes based on the reconstructions. Okay, so I hope so we'll in the next class I will just go through the calibration procedures which are very important to calibrate during the field operation and also during the reconstruction procedures. Okay, we'll meet in the next class.